Well, hello and welcome to GetChemistryHelp.com. My name is Dr. Kent. In this video, we're going to discuss how to write molecular, complete ionic, and net ionic equations. Well, your first question probably is, what's the difference between the three equations? Well, a molecular equation is the typical equation that you're used to writing. It's where you have the reactant species on the left-hand side of the arrow, the product species on the right-hand side of the arrow, and everything is balanced. This is your typical chemical reaction. However, this is not the best visual representation of what's really occurring in a reaction. So that's why we need what's known as the complete ionic equation. So for example, we know, thanks to our solubility rules, silver nitrate is actually aqueous. It is dissolved up into your solution. Potassium chloride also dissolves in water. It's aqueous. However, silver chloride is not dissolved. It stays together as a solid, while potassium nitrate is soluble. So how do we show this more accurately? Well, that's where the complete ionic or the total ionic equation comes in. So this top equation is the one you're used to seeing, which is what we're going to call the molecular equation. This new one is the complete ionic or the total ionic, and I'll put an I here. The difference is that now we are trying to represent the species the way they actually are in solution. So what that means is, if I have an ionic compound that is soluble, this ionic compound is not staying together in the solution. Once the solid dissolves in water, it does then dissociate into individual ions. So it breaks up into the silver cations and the nitrate anions. Same thing with potassium chloride. When that potassium chloride is represented here as being aqueous, that means it's soluble and it has dissolved. So it splits up into potassium and chloride ions in solution. These are the actual species in your beaker, for example. It's not a chunk of potassium nitrate and a chunk of potassium chloride. It's these individual ions. However, silver chloride, we know, is not soluble. It's a solid. So it does stay together as a single unit. So you can just bring it right on down as a solid. But potassium nitrate, again, it's soluble, which means when it dissolves into water, because it's made up of potassium and nitrate ions, those ions then split apart, or they dissociate is the fancy word for that, into potassium and nitrate ions. So this is a more accurate representation of what's occurring in solution. Now again, we do not separate solids, liquids, or gases. Those really are a single unit. Those do not dissociate into their individual ions. The only thing you're going to dissociate are soluble ionic compounds. And I'll say that again, soluble ionic compounds. So if it's an ionic compound and it's soluble, which means you write it as AQ, then you're going to dissociate those. But this means you do not dissociate molecular or covalent compounds. Those are not formed from ions. So for example, let's say we had carbon dioxide. Carbon dioxide is a molecular compound. Even if it was aqueous, dissolved in the water, you would still write it together as CO2 aqueous. Now one other little nuanced thing that I'm not really going to cover in this lesson has to do with what are known as strong versus weak electrolytes. Technically only strong electrolytes are the ones that are going to dissociate, things like strong acids, strong bases, and weak acids and weak bases, those you would not dissociate. That's another topic for another day, but I did just want to make mention of that. So for now, we're just going to treat any soluble ionic compound as something that we're going to dissociate into the ions. Okay, so now we have our complete ionic or our total ionic equation. But there's still one more step we can take, because you might notice that there are some ions that appear on both the reactant side and the product side. So for example, potassium ion is on the reactants, nitrate ion is on the reactants, and it's also on the products, which means essentially these ions aren't really contributing anything to the overall reaction. Their only role really is to help the silver and the chloride then to get in the solution. So we are going to remove those and cross those out. So I see a nitrate on the reactants and the products. I'm going to cross those out. I see a potassium on the reactants and the products. I'm going to cross those out. So whatever is left is known as the net ionic equation. So now we see that really what's occurring in this reaction are dissolved silver ions are combining with these dissolved chloride ions to form silver chloride solid. And that's what this net ionic equation shows down here. Now to give you a little better idea or visual of this, I want to draw a crude little picture here trying to illustrate this. So let's imagine this is a beaker of what's occurring when the reaction starts. So I dissolve some silver nitrate into solution, and it immediately dissociates and makes some silver ions, makes some nitrate ions, and then I also dissolve into it then potassium chloride, and that dissociates and makes some potassium ions and some chloride ions. Well, we know then from our double displacement reactions that these begin to swim around and they find new partners. So now the silver decides to partner up with the chloride instead of the nitrate, which leaves the potassium nitrate still dissolved. So now in our products beaker, it's going to look like this. Now that silver chloride has combined and made a white solid here on the bottom of our silver chloride solid. But the potassium ions and the nitrate ions, those are still swimming around in solution. So you can see then that the only species that actually contributed to the reaction were the silver and the chloride combined to make the silver chloride. Again, the potassium and the nitrate, those were there in the reactant side and they're still there in the product side. So they're not actually contributing anything to the overall equation. Again, they're just there to help the silver and the chloride get in solution. So they are our spectators. They are just the bench warmers. They are just watching the reaction and cheering on the silver and the chloride, helping them to do their thing. Okay, so let's try an example of this together. So the problem says, balance the molecular equation, then write the complete ionic and net ionic equations, including the physical states. And the reactants are iron 3 bromide and potassium phosphate. Okay, so first we want to do the molecular equations. I'll put M for molecular. So we need to figure out what are the reactants. So we use what we learned back in our lessons on formulas for ionic compounds, and we know iron 3 bromide. Well, iron 3 means it's iron 3 plus. Bromide is 1 minus, so it must be FeBr3. Then we can use our solubility rules. By the way, if you need a copy of those, you can go to Get Chemistry Help under the Resources tab and find a copy of those. And we can determine what's the physical state of this. Is iron 3 bromide aqueous? Is it soluble in water? Or is it solid, insoluble in water? So we look over here and we want to find a rule for bromide, and it says, okay, bromide compounds are all soluble or aqueous unless they're combined with silver, mercury 1, or lead 2, which ours is not. So it must be soluble, aqueous. Okay, the other reactant is potassium phosphate. So potassium has a 1 plus charge, phosphate's 3 minus. So I would need 3 potassiums to combine with the phosphate. And once more, we're going to use those solubility rules. So I want to find a rule that has potassium and or phosphate in it. So here we see potassium anything is soluble all the time, no exceptions. And down here we also see phosphates are insoluble unless they are with potassium. So this is also soluble, aqueous. Okay, now we got to predict our products. Well, we know from our lesson on double displacement reactions, we're basically just going to swap partners here. So the iron 3 is going to go with the phosphate, the potassium is going to go with the bromide. So iron 3 phosphate would have this formula, and then potassium bromide would have this formula. Okay, how about our solubility rules? Well, what's the solubility rules for phosphate? Again, we saw that phosphates are insoluble. They make solids unless they're with lithium, sodium, potassium, and ammonium. Ours is with iron 3, so it's not an exception, so this would be a solid. And potassium bromide, well, we saw potassium anything is soluble all the time, no exceptions whatsoever, so it's going to be aqueous. Okay, so now we have our products. Last step is to balance this equation. So we look over here, we got 1 iron, 3 bromides, 3 potassiums, and 1 phosphate. So we need 3 potassium bromides. So that's the molecular equation. Now the next step is to write the complete ionic, I'll put I for that, or the total ionic equation. So now we want to represent a little more clearly what species are actually in solution. Well, again, the process for this is to look for any soluble ionic compounds, and if you find one, then you're going to dissociate that into the individual ions. So iron 3 bromide, that's an ionic compound. It's soluble, so we're going to show the ions that are present. So iron 3 bromide is, of course, made up of an iron 3 ion, and it's also made up of 3 bromides. So we're going to write 3 bromides. Now a quick little tip on this, make sure you do show this as 3 bromides. One common mistake I've seen students make is they'll try and bring it down and they'll leave the 3 down here instead of putting it out front. So make sure you don't make that mistake. Okay, how about the potassium phosphate? Well, potassium phosphate's ionic and it's also soluble. We can see from the aqueous. So what ions would that dissociate into? Well, we'd have 3 potassium ions and we would have a phosphate ion. Now notice here I'm using the same physical states as I had in the molecular equation. You don't need to go back to the solubility rules and try and figure them all out again. So if iron 3 bromide was aqueous up here, then the iron 3 and the bromide is going to be aqueous here. Now on to our products. So iron 3 phosphate. Well, that's an ionic compound, but notice it's not soluble. So again, you don't dissociate solids, liquids, or gases. So we're going to write this just the way it is. Iron 3 phosphate is in fact a single unit in our solution. And then how about the last product, potassium bromide? Well, there's 3 of those. It's ionic and it's soluble. So we're going to dissociate that and show the ions. So what ions would 3 potassium bromides form? Well, it would form 3 potassium ions. And it would form 3 bromide ions. Okay, so there's our complete ionic or our total ionic equation. Well, now next we need to prepare to write the net ionic equation. That means we have to get rid of any so-called spectator ions. Again, those are the ions that appear on both the reactant side and the product side. So what ions do you see? Well, you probably noticed that there are 3 bromides on both sides and 3 potassium ions on both sides. Now a quick little tip here, these should always cancel out in the same number. If you find yourself canceling out 3 bromides on one side and then 1 or 2 bromides on the other side, odds are you've made a mistake. So either you didn't properly balance the molecular equation, or when you dissociate it up into ions, you didn't dissociate it out into the correct number of ions. So again, if these don't cancel out with the same number, go back and find your mistake. Okay, so now for the net ionic, we just write whatever is left. So after I've crossed out the spectator ions, what we had left were an iron 3 ion combining with a phosphate ion to form iron 3 phosphate solid. So this is our net ionic equation. Let's try another example. So for this one, we're going to look at sodium sulfite combining with hydronitric acid. So let's do our molecular equation first. So sodium sulfite, sodium is 1 plus, sulfite is 2 minus. So it'd be 2 sodiums with the sulfite. And how about our solubility rules? Well, we see that sodium anything is soluble, and there are no exceptions to that. So this must be soluble. What's hydronitric acid's formula? Well, hydroic must come from ide, so nitride would just be nitrogen by itself, which is 3 minus, so we need 3 hydrogens. Again, acids are soluble. We don't need to even look at our solubility rules for that one. Now we can do a double displacement reaction and swap our nitride with our sulfite. So we're going to get sodium nitride, which would have this formula. Sodium's plus, nitride's 3 minus. Sodium anything, again, is soluble, no exceptions. And hydrogen is going to combine with sulfite to make H2SO3, or sulfurous acid. Again, acids are soluble. We'll put our aqueous here. Aha, well this is one of the products you might recognize from our lesson on gas evolution reactions. So sulfurous acid doesn't actually stay as this. It's actually sulfur dioxide gas dissolved in water. So I do want to rewrite that, but I want to balance the equation first, and then I will do that next step. So let's look here and see we've got 2 sodiums on the left, 3 sodiums on the right. So we'll balance those out, make those both 6. So we'll put a 3 in front of this and a 2 in front of this. Now we've got 3 sulfites on the left, so I'll make this 3 sulfites on the right side. Then we've got 3 hydrogens here, but 3 times 2, 6 here, so I'll put a 2 here. Now we've got 2 nitrides and 2 nitrides, so we're balanced. Okay, so now I want to replace this with what is actually in solution, which is water and sulfur dioxide gas. But notice I had 3 sulfurous acids, so that's going to make 3 water liquids. That's supposed to be an L, and 3 sulfur dioxide gas. Okay, so this is the balanced molecular equation. Now let's go on to our ionic equation. Well, again, we're going to dissociate any soluble ionic compounds. So I look here and I have 3 sodium sulfites. It's soluble, it's made of ions. So what ions would that form? Well, 3 sodium sulfites. How many sodiums am I going to form? Well, it's not just 3, because each sodium sulfite has 2. So 2 times 3 is going to be 6 sodium ions. And how many sulfites? Well, I've got 3 sulfites. So 3 sulfite ions. How about this acid? Well, this is also made up of ions. Again, we're going to ignore if it's a strong or a weak acid in this lesson. We'll cover that in the future. For now, we're just going to assume it's ionic and it's soluble, so we will dissociate it. So 2 times 3 tells me I have 6 hydrogen ions, and I have 2 nitrite ions. So 2 nitrite ions. How about the product side? Well, here's another soluble, aqueous, ionic compound. So what ions will that dissociate into? Well, we got 2 times 3, 6 sodiums. And we have 2 nitrides. So 2 nitrite ions. How about the 3 waters? Well, again, we said we only dissociate soluble ionic compounds. Solids, liquids, and gases, these stay together as a single unit. So this is a liquid, so 3 waters. We just write it again as 3 waters, liquid. And 3 sulfur dioxide gas, we write that again as 3 sulfur dioxide gas as a single unit. Okay, now for the net ionic. Well, first we have to get rid of any spectator ions. So are there any ions you see that appear on both the reactants and the product side? And hopefully if we did this right, they're going to be the same number on both sides. Well, I see 6 sodiums on the reactants and 6 on the products, and I see 2 nitrides on the reactants and 2 nitrides on the products. So now we're going to write whatever is left. So 3 sulfite ions react with 6 hydrogen ions to form 3 water liquid and 3 sulfur dioxide gas. So you would normally stop there, but you might notice this is not balanced with the simplest whole number ratio. So we are going to do one more step, and we're actually going to reduce this. So instead of 3 to 6 to 3 to 3, the simplest ratio would be 1 to 2 to 1 to 1. So I'm going to go ahead and write that as sulfite reacts with 2 hydrogen ions to make water liquid and sulfur dioxide gas. Well, there you have it. Now notice the equation should of course still be balanced after you've gone through all of these steps. So we got a sulfur and a sulfur, we've got 3 oxygens, we got 1 plus 2, 3 oxygens, 2 hydrogens, 2 hydrogens. Yep, it's still balanced, so everything looks good. Well, let's try one last one just to make sure we got it. So now we're going to do phosphoric acid neutralizes a sodium hydroxide solution. So we'll start with our molecular equation. Phosphoric acid, ic comes from 8, so phosphate. Phosphate's 3 minus, so it needs 3 hydrogens. Sodium hydroxide. Sodium is plus, hydroxide's minus, so 1 of each. If you look at our solubility rules, again we know, sodium anything. If you look at our solubility rules, again we know sodium anything is soluble, no exceptions. And then we're going to predict our products. So we're going to swap out the phosphate with the hydroxide. And notice this is an acid-base reaction. So when hydrogen and hydroxide combine, That makes water. And then we're left with sodium and phosphate. So sodium phosphate, sodium phosphate. And again, sodium, anything is soluble, no exceptions, so aqueous. Well, let's balance this equation. Again, if you remember our lesson on acid-base neutralization reactions, one little tip on balancing these kind of reactions is to think of the water as really being composed of a hydrogen ion with a hydroxide. So I see 3 hydrogen ions here, so I want 3 hydrogen ions here. But now I need 3 hydroxides, so I'm going to put a 3 here. So I effectively have 3 waters, because 3 hydrogen hydroxides is 3 waters. And now we're balanced. Okay, now the ionic equation. Again, you want to dissociate anything that is a soluble ionic compound. So this is soluble. It's made up of ions, hydrogen ions and phosphate ions. So what would that dissociate into? Well, we'd make 3 hydrogen ions, and we would make a phosphate ion. Okay, how about the 3 sodium hydroxides? Well, it's also soluble and it's ionic, so it'll make 3 sodiums and 3 hydroxides. So we'll write 3 sodium ions and 3 hydroxide ions. How about the liquid water? Again, we don't dissociate solids, liquids, or gases, only if it's ionic and soluble, so we'll just leave that together as 3 water liquids. Sodium phosphate, well, that is ionic and it's soluble, aqueous, so we will dissociate that. So that'll form 3 sodiums, so 3 sodium ions, and 1 phosphate ion, also soluble. So next, we're going to identify and cross out any spectator ions. So what ions do you see on both the reactants and the product side? Well, I see a phosphate on both sides, and I see 3 sodiums on both sides. So now for the net ionic, we write whatever is left, which was 3 hydrogen ions combining with 3 hydroxide ions to form 3 water liquids. But one last little step, again, this is not the simplest ratio, 3 to 3 to 3. So we're going to reduce that down to hydrogen ion plus hydroxide ion combined to form water liquid. Well, I hope you found this lesson helpful. If you did, be sure and hit the like button and also subscribe to the channel so you never miss any future videos. You can also come over and visit me at getchemistryhelp.com for even more free videos, worksheets, and other resources to help you succeed in chemistry. Have a great day.